Every second, over 100,000 Google searches happen, 4 million YouTube views are watched, 200 million emails are sent. The internet has become as essential as electricity, yet most of us don't understand how it actually works or how we got here. Well, this is the story of humanity's most transformative invention since the printing press, a journey from a Cold War experiment connecting 4 computers to a global network of 5 billion users. This is the Internet Revolution. October 29, 1969, UCLA's Computer Lab. A team attempts something never done before, sending a message from one computer to another, 350 miles away, at Stanford Research Institute. Now, the programmer types LOG, and the system crashes, but they've just transmitted the first 2 letters ever sent over what would become the Internet. This was ARPANET, the Advanced Research Projects Agency network. Funded by the U.S. Department of Defense during the Cold War, it had one goal: create a communication network that could survive a nuclear attack. By the end of 1969, 4 universities were connected. The network worked, but each computer spoke a different language. Enter Vint Cerf and Bob Kahn, 2 engineers with a radical idea. What if all computers agreed on one universal language? In 1974, they published a paper describing TCP/IP, Transmission Control Protocol, and Internet Protocol. Think of it as the Postal Service for digital information. Here's how it works. When you send data, TCP breaks it into small chunks called packets. Each packet gets wrapped in an IP envelope containing the sender's address, the destination address, and instructions for reassembly. These packets then travel through routers, specialized computers that read each packet's destination and forward it along the most efficient path. Now, if one route is congested or broken, the packets simply take another path. This is fundamentally different from a phone call. A phone call requires one dedicated line for the entire conversation. The internet shares the same wires among millions of users simultaneously. It's the difference between reserving an entire highway for yourself versus all cars sharing the road. On January 1, 1983, ARPANET officially switched to TCP/IP. This date marks the true birth of the internet as we know it. But there was a problem. Every computer on the internet has an IP address, a string of numbers like 172.217.164.142. Imagine memorizing these for every website you visit. In 1984, Paul Macapetris invented the Domain Name System, DNS. It's the internet phone book, translating human-readable names like Google.com into machine-readable IP addresses. Every time you type a web address, your computer asks a DNS server, "What's the number for this name?" It happens in milliseconds, and it's all invisible to you. By 1989, the internet connected thousands of computers, but it was text-based and difficult to navigate. Enter Tim Berners-Lee, a British scientist at CERN who asked a simple question: what if information could link to other information? In 1991, he launched the first website. It was just text and hyperlinks, but it introduced 3 revolutionary concepts. HTML, Hypertext Markup Language, formats how pages look. HTTP, Hypertext Transfer Protocol, how pages are requested and delivered. And URL, Uniform Resource Locator, the address of each page. HTTP is your browser's way of asking a server, "Please send me this page." The server responds with the HTML code, images, and styling instructions. Your browser assembles it all into what you see. In 1993, the Mosaic browser made the web visual and accessible. By 1995, Netscape went public, and the dot-com boom began. The internet was no longer for scientists and hobbyists. It was for everyone. But there was a bottleneck: speed. Early internet connections used dial-up modems over phone lines, maxing out at 56 kilobytes per second. Downloading a single song took 20 minutes. Understanding internet speed requires knowing 2 concepts: bandwidth and latency. Bandwidth is how much data you can transfer per second. It's the width of your pipe. Latency is how long it takes for data to make the round trip. It's the delay before transfer begins. Broadband, DSL and cable modems increased bandwidth by 200 times. Suddenly, streaming video became possible. Downloading a song took seconds, not minutes. And by the mid-2000s, YouTube and Netflix emerged. The internet wasn't just about reading anymore. It was about experiencing. June 29, 2007, Steve Jobs holds up the iPhone. For the first time, the internet isn't tied to a desk or a cable, it's in your pocket. Mobile internet didn't just add convenience, it fundamentally changed what the internet was for. Apps replaced websites, social media became constant, not occasional. The internet became omnipresent. But all these mobile devices created a problem. They're not powerful enough to handle everything we need. The solution? Move the computing power back to the internet itself. In 2006, Amazon launched AWS, Amazon Web Services, renting out their massive computer infrastructure. Google, Microsoft, and others followed. This is cloud computing. Your data and applications don't live on your device. They live on thousands of servers distributed globally. Whenever you share a file on SharePoint or edit a Google Doc, the actual processing happens in a data center. When you stream on Netflix, the video is served from the closest server to minimize latency. Your device is just a window into computers elsewhere. In 1995, Amazon sold its first book online. Today, global e-commerce generates $5.8 trillion annually. The internet didn't just add another sales channel, it obliterated geography. A craftsperson in rural India can sell to customers in New York. A teenager in their bedroom can launch a global brand. The internet democratized access to markets in a way previously impossible. But there's a technical foundation. Inventory databases synced in real time, payment gateways encrypting transactions instantly, recommendation algorithms processing millions of data points. E-commerce only works because the internet can handle massive, simultaneous transactions reliably. Netflix was founded in 1997, allowing subscribers to rent unlimited DVDs for a flat monthly fee. With that, they laid the foundation of what would become the new standard for video, made possible by broader and faster connectivity worldwide. In 2007, Netflix began streaming content over the internet, and slowly but steadily, cable TV was dying. And while cable TV is still available today, approximately 80% of internet traffic is video streaming. Now here's the magic. Streaming doesn't download the entire video first. It sends small chunks continuously, adjusting quality in real time based on your bandwidth. If your connection slows, the quality drops seamlessly. This is adaptive bitrate streaming. And Netflix doesn't stream from one location. Their content lives on thousands of servers worldwide, provided by internet service providers. When you watch, it comes from the closest server, minimizing latency and maximizing speed. The technical breakthrough wasn't just faster internet, it was smarter distribution. March 2020, the pandemic sends millions home, and within weeks, remote work becomes normal. This wasn't possible even 10 years earlier. What followed was an increase in connecting online. Colleagues started using video conferencing tools like Microsoft Teams and Zoom for meetings, enabling them to continue. Collaboration almost completely moved to cloud storage platforms like Google Drive, SharePoint, and Dropbox. And for project management, whole organizations that weren't already using them started moving to platforms and tools like Azure DevOps, Atlassian Jira, or Trello. With more online connectivity, digital security and safety became even more important, and the use of VDIs and VPNs increased drastically. Remote work requires multiple technologies working flawlessly together. High bandwidth connections for video, low latency connections for real-time collaboration, secure cloud storage, and reliable uptime. Now, it wasn't only work that caused the 40% overnight increase in internet traffic. Since going out wasn't an option, many people turned to online gaming, and games like Among Us became a sensation. The humorous and social interactions online were much needed for everyone globally, and it was all because the infrastructure held. Thanks to decades of overbuilding capacity and distributed architecture, the internet was designed for resilience, and it proved it. The internet is evolving again. We've had Web 1.0, static websites you could only read. Then Web 2.0, interactive platforms where you create content, but companies own it. Web 2.0 centralized power. Facebook owns your social graph. Google owns your search history. Amazon owns your purchase data. Web 3.0 proposes a different model, decentralization through blockchain. Instead of data living on company servers, it lives on a distributed network. You own your data. You own your digital identity. Cryptocurrencies like Bitcoin demonstrate this. Transactions happen peer-to-peer, verified by thousands of computers worldwide, with no bank in between. NFTs, decentralized social networks, and blockchain-based services are all early experiments in this vision. But Web 3.0 faces challenges. Blockchain is slow. Bitcoin processes 7 transactions per second versus Visa's 24,000. It's energy intensive, and it's complex for average users. Now, whether Web 3.0 fulfills its promise or becomes a niche technology remains to be seen, but it represents the internet's next ideological frontier. Who controls the network? As many people believe the internet is the web, it's only the infrastructure. The network of networks. The World Wide Web is just one service running on the internet, alongside email, file transfer, gaming, and streaming. Tim Berners-Lee invented the web, not the internet. Wi-Fi is just a wireless connection between your device and your router. The internet is a global network your router connects to via your ISP's cables. No Wi-Fi doesn't mean no internet. You could plug in with an Ethernet cable. No ISP connection means no internet, even with perfect Wi-Fi. Your internet speed is actually two things. Bandwidth, measured in megabits per second, is your capacity. Latency, measured in milliseconds, is your delay. For streaming, you need high bandwidth. For gaming or video calls, you need low latency. That's why satellite internet often disappoints despite high bandwidth. The signal traveling to space and back creates 600 plus millisecond latency, from 4 computers to 5 billion users, from 56 kilobits per second to gigabit fiber, from static text pages to immersive virtual worlds. The internet hasn't just changed how we communicate, it's changed how we learn, work, create, love, and organize society. It's dissolved borders, democratized information, and connected humanity in unprecedented ways. And at its core, it all comes back to those packets, small chunks of data, each finding its own path, reassembling at their destination. Simple, resilient, revolutionary. Now, the internet story isn't finished. As we stand on the edge of Web 3.0, artificial intelligence, and technologies we can't yet imagine, one thing is certain. The next revolution is already being written in code somewhere. And the internet revolution isn't just about technology. It's about human ingenuity, collaboration, and our endless drive to connect with one another. From ARPANET to Web 3.0, we've built something remarkable. What we build next is up to us.